This is Derek, and this is section 4.4, equations involving roots and rational exponents. So this will be solving. So these first ones are pretty friendly. It's just kind of getting you set up with the idea as to how to work with roots and powers. And basically roots and powers are going to be inverse operations to each other. So, and we've seen this when we had a square root, we would square it to undo. Likewise, cube root, we would cube it to undo. And that's basically what we're going to do here. If I have x to the 1/5 equals 7, this 1/5 is the same thing as a fifth root. And so what I would do is I would raise it to the 5, right, or to the 5th. And then what I do to this side, I have to do to this side. And then 1/5 of 5 will be x. And then 7 to the 5th comes out to some big old number, 16,807. This is basically the same problem. I just wrote it in the other notation and threw a 2 on this side. So if I have the 5th root of x, again, I can raise it to the 5th. And what I do on this side, I have to do over here as well. So same thing, just 2 different notations. And that will still be an x, and then 2 to the 5th is 32. This time we have an x to the 5th, as opposed to the 1/5 to the 7. And so now that this is a integer, we're going to take the root. So you can see we're just kind of forwards and backwards on these. So if I take the 5th root of both sides, then on this 5th root of 5 gets plain x. 5th root of 7 is the 5th root of 7. And on this one, let me write that a little bit bigger. X to the 2/3 equals 9. So I could undo these at the same, I could raise both sides, cube both sides, and then root both sides. But an easier way to think of it with this fractional exponent is I just really want the exponent to be 1, so I'm going to raise it to the reciprocal. And then here when we multiply, we would get x to the 6/6, which is just 1. And then that means we just need to simplify this side. So 9 to the 3/2 would be the same thing as square root 9, because that 2 is a root, and then cube that result. So square root of 9 would make a 2, and then cubed will make, 3 cubed will make 27. Okay, so equations involving radicals. Our steps for these are going to be to isolate the radical first, and then we're going to raise both sides of the equation to the index. So that's kind of what we're doing back here. So if it's a cube root, I would cube both sides. A square root, I'll square both sides, etc. Step 3 is just kind of a little reminder on how to solve. If you get a linear equation, remember with that we're getting x's to one side, numbers to the other. If we get something quadratic, which we will at least one of the examples, we're going to factor, and then that's how we'll solve. And then for even roots, we do have to be careful that we can pick up, when we square both sides, we can pick up a fake answer. The reason for that is, say I have 2 equals -2, which is totally not true. But if I square both sides, then I have 4 equals 4. So I can take something that's untrue, square it, and make it true. So by squaring both sides, I can pick up what's called an extraneous solution. And so what we're going to do is we're going to check that all of our answers work on the even roots. So let's start off with this example. First thing I'm going to do is try to isolate the radical. So I'm going to subtract the 7 over. So that's going to leave me 3, and then square root x minus 4 equals, that would be 18. And I could square both sides now, but I think it'll be way easier if I get rid of that 3 first. So now I have root x minus 4 equals 6, and now when I square it, it's not a giant number. And so we'll square, so now we're squaring to undo the radical. That gets us x minus 4 equals 36, and then add the 4 over, and x equals 40. So then if I check that, I'll do it right up here because I didn't leave myself very much room. 7 plus 3 times, this would be 40 minus 4, should come out to 25. So let's see, 40 minus 4 would be 36. Square root of 36 is 6. So that'd be 7 plus 3 times 6 is 18, and there's our 25. So it does check in the original equation. This one, let me write that a little bit bigger because it's a fifth root and it's hard to see. And so it's already isolated, and this time it's a fifth root, so I want to raise it to the fifth power to undo that root. And those are taken care of, so 9x minus 8 equals 32, and then we will add our 8. That's going to be 9x equals 40, and then divide out the 9. There's nothing common between 40 and 9, so that's already reduced, and that is as good as that would get. This one we don't have to check because it's an odd root. And so with odd roots, if I had 2 equals negative 2 and I cube both sides, I get 8 equals negative 8, and it doesn't get any truer. So for the odd roots, we don't pick up the extraneous, but for the even roots, we do. And then this one right here has root equals negative 9. There is, with all that in there, it's a little bit hard to see, but think about if it was just root x equals negative 9. If I put in 81, I get 9. If I put in negative 81, right now I get, it doesn't exist, which it's really not a real solution. It's going to involve imaginary numbers in the next chapter. And so there is no solution to this, so we would just say D and E for now. Okay, so for this one, the radical is isolated, so I will square both sides. Square undoes root, so I get x plus 23. Over here, careful to FOIL that out and not go x squared plus 9, because that's totally make-believe math. So it's going to go x squared, we'd have an outside and an inside that would get us a 6x when you do your FOIL, and then plus 9. This is one where it does come out quadratic, so when it's linear, again, x is to one side, numbers to the other. But for quadratic, we want to get everything over to one side so that we can either factor or use quadratic formula or some other method of solving. These ones will factor. So those drop out, that drops out, we got our 0 over here. And then this is going to go x squared, and then 6x minus x would be 5x. 9 minus 23 gets us a minus, what is that, 14? Yeah. And then we can factor that. So we're looking for two numbers that multiply to be negative 14 and add to be 5. So that sounds like a positive 7 and a, negative 2. So that gives us potential solutions of x equals negative 7 and x equals 2. But then this is where we have to check them. So coming back to my original equation, if I go negative 7 plus 23 equals negative 7 plus 3, right there you can see it's not going to work because it's equaling a negative number. And root 16 is 4, not negative 4, so that one is extraneous. If I toss a 2 in there, let's see what happens. So 2 plus 23 is supposed to make plus 3. That is square root of 25 equals 5. That one's legit. So x equals 2 is our only solution. Okay, these next couple are examples involving radicals or rational exponents, but they're going to be able to factor, so they're in the form of a quadratic. A great way to look at these is if you can square whatever's in the middle and it makes whatever's in front, that means it's in the form of a quadratic. So root x squared would make a plain x. When you see that, what that means is whatever's in the middle is how it's going to split the factor. So if I did a problem that was like, say I had x squared plus 2x minus 24, I would look at this, and this x tells me it's going to split up x and x, because x times x makes x squared. When we add them, that gets us cross terms. Same thing here. So this is going to be square root and square root. And then root x times root x, there's our x. So always look in the middle to figure out what to do in that spot. And then same thing here, we would say what multiplies to negative 24 and adds to be 2. Nothing's changed, it's just now it's the powers look a little bit harder. So this would still be a plus 6 and a minus 4 to make the negative 24 and add to the 2. When we go to solve, that's where this is a little bit different from down here. So root x plus 6 equals 0. When I bring that 6 over, there we are at that same place where I have square root equals a negative, which doesn't work, so that one's extraneous. Here we have square root minus 4 equals 0. Add the 4 over. Root x equals 4. Now I can square both sides, so that's legitimate because of there's no negative, and x equals 16. This next one's pretty similar, except it's in fractional form instead of root form or radical form. So the 1/3 in the middle, that x to the 1/3, this is x to the 2/3 here, it's a little bit small. That again is going to tell me how this is going to split. So if I go x to the 1/3, x to the 1/3, oops, I'm going to scoot this 10 over so it will be, I should have written that out. So I forgot that step to bring the 10 over first. But if we go x to the 1/3 times x to the 1/3, we would be adding those exponents, and that's how we get back to the 2/3. And then here we're just looking for two numbers that multiply to be -10 and add to be +3. So that's going to sound like a +5 and a -2. Should get that one done. And now we just solve each of these. So x to the 1/3 plus 5 equals 0. X to the 1/3 equals -5. And then we will cube both sides because we're undoing a 1/3. And again, since these are odd roots, no troubles with extraneous solutions, everything will work. So that makes x equals -125 for that branch. And then over here, 1/3, I'll just add the 2 over as I go. And again with cubing. And then that's going to get us x equals 8. Okay, next topic is just a little review of Pythagorean theorem. So you've probably run into this somewhere before, but if we have a right triangle, which just means we have one 90-degree angle in there, if we go a squared plus b squared, where a and b are the legs, that will equal c squared, which is the hypotenuse. And so let's see how that will look with a few words. 12-foot ladders placed against a building. If the base of the ladder is 5 feet away from the building, how far up the building will the ladder reach? And round to the nearest tenth. Okay, so let's do a little sketch. There's our building. There's our ladder. And the ladder, it tells us, is 12 foot. And the base is 5 feet away from the building. And so what we're trying to find is how far up can we reach? So this is going to go a squared plus b squared is 5 squared equals 12 squared, because that's our hypotenuse. So a equals 12 squared is 144, and then I'm going to subtract that over minus 25. Oops, sorry, a squared. And that would make a 119 there, and then I just threw that in the calculator, and I got a to be 10.9 feet to the nearest tenth. Okay, and the last up, we got a couple of applications, pretty straightforward. So the wind speed in miles per hour, V, required for a wind turbine to generate P watts of power can be determined using that formula. How much power can be generated when the wind speed is 30 miles per hour? Okay, so our velocity is 30. And that's a little cube root in there in case you can't see. We're solving for how much power. So that's the P. And then 0.015. So to solve that, we are going to add a cube root. So we're going to cube both sides. I'll sneak over here with it. So 30 cubed is 27,000 equals P over 0.015. And then we'll just multiply both sides by that 0.015. And then those cancel, and so then we get P equals, what did I get there? 450 watts. And then part B is just take this formula and solve it for P, which I actually wish they had done that first, because then we could have just plugged this in and not gone through all the solve. But I guess it kind of helps to see the way we would solve this with numbers is the exact same way we would solve it with just the variables. So let me rewrite this a little bit bigger right here. And we will cube both sides. So v cubed equals p over 0.015, and then just multiply that up. So then that would be p equals 0.015 v cubed. And that would be this solved around for p. And then this last one's really similar. If a gun is fired vertically into the air, the time it takes the bullet to return to the ground is given approximately by this formula, where h is the greatest height the bullet reaches in meters, g is the force of gravity, which is 9.8 meters per second squared. If the bullet returns to Earth in 10 seconds, what is the greatest height that reached around to one decimal place? So same idea, we're just solving for that h there, given a known time. So this would be t equals 1/2 root 2h, and then gravity is 9.8. So I would multiply both sides by 2 first, and then I don't have to contend with that fraction. Now it'll give me 20 equals root 2h over 9.8. Now we'll undo the roots. We're going to square both sides and pop up here with it, just have a little more room. That'll be 400 equals 2h over 9.8. And then to get rid of the 2 and the 9.8, I could reduce that and get a 4.9 there. That would be one way. I could also just do 9.8 over 2, and then 2's cancel, 9.8's cancel. Or you could do 2 steps if you're more comfortable. And then 2 goes into that, be 200 times the 9.8. And for that, I got, what did I get? 1960. And that was our h. And then here, same thing, we're just going to solve the formula for h in terms of g and t, so we're not going to use the 9.8 for that g. We're just going to leave it as a variable. So this would be t equals 1/2 root 2h over g. So I would do the same thing. I'd multiply both sides by 2. So that will give me 2t equals 2h over g under a radical. And then let's square both sides of that. Careful to get that 2 squared, not just the t, because we're squaring the whole side. And that will give me 4t squared equals 2hg. And then we can multiply up the g. I'll come right here with it. So that's going to be 4t squared g equals 2h. And then let's divide out that 2. So 2t squared g equals h. And once we're there, and that's where I kind of wish they had us do this first, then we could just plug these in, and then we would have got the h without all the solving.